So, we have mentioned already that the Navier-Stokes equations, which of course are the governing equation for all fluid motions, are extremely difficult to solve because of its nonlinear nature, and often the boundary condition is quite complex, nonlinear as well, and in general we do not have solution available for the Navier-Stokes equations. So, the next we try to see whether this equation can be simplified, and then if it is, then under what condition, whether some term from this equation can be dropped or can be neglected. And to do this, the straightforward or easiest approach is a dimensional analysis of this equation, okay. Because if we express the equation in a non-dimensional form, we will be able to compare different terms present in it, and if we find that one term is much smaller than the other terms, we can drop that term. And with that view, now we will look for the non-dimensional form of these Navier-Stokes equations. Now, if we consider incompressible flow, incompressible or constant density flow. You know, the governing equations are the continuity equation, which gives divergence of the velocity field, which is okay. In Cartesian system, you can write du dx plus and the momentum equation, which is to non-dimensionalize these equations. Okay, we need not consider the energy equation, as we have already mentioned that the energy equation is decoupled in case of incompressible flow, and these two equations can be solved independently. Once these are solved, the velocity field can be used to solve energy equation in case it is required, I mean in case we are interested to solve it. Now, to non-dimensionalize this equation, we have to consider certain reference quantities or characteristic quantities. The characteristic quantities or reference quantities are of course problem specific, but we can take some general cases, like for the length we can consider a characteristic length, and this characteristic length we mean that a length over which a considerable change in the parameters are observed. So, as an example, if we are consider flow around a circular cylinder, then the cylinder diameter can be taken as the reference length or the characteristic length, because if we consider a length of that amount, we will see that within that length a considerable change has occurred in all other parameters. So, that will be taken as a consider reference length or characteristic length. In case of a flow over an aircraft, we can consider the wing chord as the reference length. So, reference or characteristic quantities, let us say for length we will take only one length L. That means, inherently we are assuming that the flow field has same characteristic length in all directions. See, in a practical flow problem, this may be different in different direction. As an example, let us say that the problem that we talked about yesterday, that flow between the two channels, or say suddenly flow about a suddenly started plate. In that case, the length of the plate in that direction there was no change. So, that is not exactly the characteristic length, rather the characteristic length is normal to the length. Okay. In case of that flow between two plate, we can consider the spacing between the two plate as the characteristic length, and in case let us say that there is also a pressure gradient in that problem, we did not use pressure gradient, but if there are a pressure gradient, then there will be a variation in flow velocity along the x direction as well. And in that case, the characteristic length in the x direction or in the flow direction and in the normal direction need not be same. However, in this case we are considering the characteristic length in all the directions are same and it is L, whatever that L is, L will be appropriately chosen in a particular problem. As far as the velocity is concerned, you see that most often we are interested in a problem where there is a flow over a body or through a body, just simply a flow that a fluid is moving, that is not of any practical interest. So, usually when the fluid is moving over some body or moving through certain body, that is what is the interesting case, that is what we are interested in. So, and when the fluid is moving over the body, its velocity is continuously changing. So, the characteristic length or characteristic velocity will consider the velocity which it would have if there are no disturbance. So, if we consider an aircraft, as you know that aircraft is moving with a certain speed, and in our aerodynamical problem we study it that the aircraft is at rest, the fluid is moving with that speed, and that we consider without the absence of the aircraft, that the air as if the air was moving with that speed when it was not disturbed by the aircraft, which we call the free stream speed or undisturbed stream velocity. So, this undisturbed stream velocity we can take as an characteristic or reference velocity. So, for velocity we use a undisturbed stream, and the undisturbed stream is usually denoted by this notation u with the suffix infinity. That means, what is the flow velocity at infinity where there is no disturbance. For time also you consider a characteristic time, again the characteristic time is a time length of time over which considerable changes in the flow takes place. As an example, let us say that if the flow is somehow periodic, then that period can be taken as the characteristic time, because over that period, let us just take it for granted that the pressure or the flow velocity or the problem is such that velocity at any point is varying sinusoidally. Then the period of that sine wave we can take as the characteristic time scale, because over that time a considerable change is taking place. This time. Similarly, for pressure also we take it like the undisturbed pressure or some reference pressure, let us call it P 0, and for the body force also we take it a body force F 0. Say as an example we can tell it this is, if this body force is gravitational force, perhaps we can take the gravitational acceleration on the surface of the earth as the reference, and we non-dimensionalize all other gravitational force in terms of that. So, with this characteristic scale we can express all non-dimensional parameters, that is we will have now the x non-dimensional version of x will denote as by x star is simply x by L. This x star is non-dimensional x. Similarly, y star is y by L. Now, let us see what happens to the equation with this non-dimensionalization. Let us start with the continuity equation. Our continuity equation is du dx plus dv dy plus dw dz equal to 0. What will happen to it? You can replace u by u star into u infinity and similarly x by x star L. So, what will you get? See, this will become du dx will become u infinity by L du dx, this will become u infinity by L Okay. So, this entire equation you can write as in the standard vectorial notation we can write once again this divergence is calculated with respect to these x star, y star, z star. Now, look into this equation, we see that we cannot find any situation where we can say that this term, one term will be larger than the other. In a general situation, we cannot tell that one term will be larger than the other, much larger than the other. because all are multiplied by the same non dimensional parameter, sorry not non dimensional, some u infinity by L a dimensional parameter multiplied by the same parameter, and all are similar type of term. So, there is no way by which we can say that one term will be much larger than the other. There is, we cannot find any condition in which that will happen. So, what we can see that there is no possible way to simplify the continuity equation, whatever it is, it is. We cannot simplify it. Now, let us come to the momentum equation. And for momentum equation, say let us say instead of taking the complete vector equation, take only the x component of the momentum equation. Consider the x component of the momentum equation, which we will call x momentum equation. The x momentum equation is rho du let us say the x component of the body force is f x, the x component of gradient of p is dp dx, and this is mu So, now if we express in the non dimensional form, what do we get? What will happen to this first term du dt? This will become u infinity by t into du star dt star. Okay. What is the second one? The second one will be u infinity square by L sorry u star, I missed it there. Okay, I will write the u star later. The second one will also be again u infinity square by L multiply throughout by L into rho u infinity square. Multiply throughout by L into rho u infinity square. The idea is to make the coefficient of these terms as 1, coefficient of these terms as 1. L upon rho u infinity square. So, what happens to the first term, the time derivative term? The time derivative term becomes L by u infinity t into we have made the coefficient of all these as 1. What is this? L is getting cancelled, P 0 by rho infinity square this is not u infinity square, no, this is not u infinity square, this should be u infinity, the second derivative. When we express the second derivative in that form, there will be no square of u infinity. L will be square because it is second derivative with respect to space. So, it is square of L, but the function itself u, that will not be square. So, it is u infinity, make that correction. So, when we multiply by that as L by rho infinity, we get mu by rho u infinity L, and instead of writing this lengthy expression, we will write again Laplacian, but Laplacian with respect to this coordinate. The y momentum and z momentum equation can also be written exactly like this. Okay. The y momentum and z momentum equation can also be written exactly like this, and again you will see that the corresponding terms are multiplied by the same numbers. That is, the time derivative term will be multiplied by L by u infinity t, whether it is y momentum or z momentum. The body force term will be multiplied by L f 0 u infinity square. The pressure term will be multiplied by P 0 by rho infinity square, and the viscous term will be multiplied by mu by rho infinity L. Now, if you look to these multiplicating factors, there are 4 multiplicating factors here, 1, 2, 3, 4. Okay. And all these multiplicating factors are themselves non-dimensional. L by u infinity is a non-dimensional, a ratio of length and length. This is L f 0 by u infinity square, that is also same thing, square of velocity. The numerator is also square of velocity, denominator is also square of velocity. Here P 0 rho u infinity square is also have a dimension of pressure, rho u infinity square also has a dimension of pressure. So, that is also a non dimensional pressure or ratio of two pressure, and here also if you see this mu and this rho u infinity L, they have same dimension. The dimension of mu and rho u infinity L has the same dimension. So, all these multiplicating factors are non dimensional factors and they are given special name. Taking this time period as inverse of frequency, time period is of course inverse of frequency. So, we can write it as frequency what to write for frequency. Conventional notation of course for frequency is f, but already we are using f as the body force. So, let us don't use f. What other symbol we can use for frequency? Nu. Nu we used for that kinematic viscosity mu by rho, which is present in this equation also. So, in the same equation using two notation for two different meaning. Omega we use restrict it for vorticity, because this frequency we are not going to use it much. You can write n equal to 1 by t. So, the first term, first non dimensional factor is n L by u infinity. This non dimensional parameter is called as Stahel number. And you see that the time derivative term is multiplied by this Stahel number, and from there we can say that if Stahel number is extremely small, that is if the frequency is very small, that there is some unsteady phenomena, but the frequency of it is very small, extremely small, then perhaps we can neglect the time derivative term. If the Stahel number is extremely small, we can restrict the or neglect the time derivative term. So, unsteady flow in which the frequency of change is extremely small, like something which changes over say perhaps 2 days or 3 days, you can neglect in that situation, or in some problem really say we are interested what happens in few seconds, and in that case we see that there is some unsteadiness, but which changes over some minutes, but we are interested in seconds, then we can forget about that time variation, we can neglect. So, when Stahel number is very small, Stahel number and is denoted by St standard. There might be other notation also used for it, but whenever we will use St Stahel number. So, we get one condition that if Stahel number is very small, we can neglect the time derivative term, or we can treat the problem as steady flow problem. Look to the now body force term which contains what? L f 0 by u infinity. L f 0 by u infinity. Consider now this body force to be gravitational. Consider only the body force to be gravitational. So, the parameter becomes what? L, that g 0 we will call it the gravitational acceleration on the surface of the earth, This is the square of the inverse of Froude number. So, if the Froude number is very small, then of course, the gravitational force must be included, while if the Froude number is very large, then the gravitational force can be neglected. The next non-dimensional parameter that comes associated with the pressure term, the reference pressure by this is usually called as the Euler number. This P 0 is, as I mentioned, that often it is the pressure in undisturbed condition, undisturbed pressure. So, P 0 is often is P infinity. A more popular or very important number, coefficient of pressure C p, which is P minus P infinity by half rho u infinity square. This is a parameter which perhaps every day we will use. Of course, as far as the magnitude is concerned, based on this we are not going to neglect pressure, because no condition will come where we will be able to neglect pressure in general. Now, look to the last term, the viscous term. The multiplicating factor is there, mu by rho u infinity L. That mu by rho u infinity L is inverse of Reynolds number. Rho u infinity L by mu is the Reynolds number. So, mu by rho u infinity L is the inverse of the Reynolds number. R is Reynolds number, Cp is pressure coefficient, coefficient of pressure. Okay. Now, immediately we get that when Reynolds number is large, when Reynolds number is very large, you can see that the viscous terms are will become very small. So, in a situation where Reynolds number is very large, we will be able to neglect the viscous term totally. We should be able to neglect the viscous term totally, because the viscous stresses will be very small and viscous forces are negligible compared to the other forces. And we see that is the situation almost in entire aerodynamics. Think about the Reynolds number of an aircraft. Assuming that even an aircraft is flying at about, say, about not exactly, at about 1000 kilometer per hour, it can be more, it can be less, little, about 1000 kilometer per hour, and the characteristic length, that is the wing chord, is up few meter. Air density is extremely small, and particularly at high altitude it is still smaller. That coefficient of viscosity is also very small. Mu for air under standard condition is about 1.789 10 to the power minus 5 kg per meter second. So, that coefficient of viscosity is of the order of 10 to the power minus 5. So, U infinity and L are large, rho is small, all right, but mu is of the order of 10 to the power minus 5. As a result, Reynolds number for the practical aerodynamical problem are of the order of 10 to the power 7, 10 to the power 8 and so on, which is extremely large, and inverse of it is practically 0. So, in most of the aerodynamics perhaps we can neglect the viscous term. So, when we will say the flow is inviscid, that is what we will mean, that the Reynolds number is very large, okay. That the Reynolds number is very large. We took an example for aircraft, but see this may be even true for many other cases, even in other fluids, like say as in case of a water, usually anything moving through water will not have that high speed, okay. Even if we consider a submarine or ship, that will not have that high speed. However, the density of the water is much larger, while it is of the order of 1 for air, it is of the order of 1000. And the ship and submarine, they can have very large length, they are very long. So, the L is quite large. Mu is of course for water also it is small and but higher than air. However, all combination again can give a very high Reynolds number. So, it is possible even in say water flow in some cases to neglect the viscous term. Anyway, whenever we may say that the flow is inviscid, the meaning is that the Reynolds number is too high. Do not think it any time that the coefficient of viscosity is 0, that mu is 0 and the flow is inviscid. No, mu is never 0, okay. There is a superfluid, some variant of helium at 2.18 Kelvin, which is a not practical case. 2.18 Kelvin, that is very close to absolute 0, one particular variant of helium shows viscosity 0, that is the only case, otherwise viscosity is never 0, but it is in general it is quite small. Viscosity, coefficient of viscosity for most of the fluids is quite small except certain highly viscous fluid, viscosity for common fluids are quite small, but anyway we never mean that coefficient of viscosity is 0. We talk about inviscid flow, but that does not mean that the coefficient of viscosity is 0. Coefficient of viscosity is small, as well as the velocity gradients are also small, and as a result the viscous stresses are small. This is the situation happens when the flow Reynolds number is very high. When the flow Reynolds number is very high, in most usually you will find that the velocity gradient are quite small and coefficient of viscosity is also quite small, and consequently the product coefficient of viscosity and the velocity gradient that gives the stress, that is small and hence negligible. So, inviscid flow never is flow with coefficient of viscosity 0, no. Anyway, in such cases the equation will become that is all, mu Laplacian u is dropped. This is the governing equation or the momentum conservation equation for inviscid flow, and this equation is named as Euler's equations. So, inviscid form of the Navier-Stokes equation is called the Euler's equation. When the viscous terms are dropped from the Navier-Stokes equation, the resulting equation is called the Euler's equation. Looking to this equation, how much simplification we have achieved? Have you achieved a very great simplification? To be precise, really no, we have not achieved great simplification. Okay. It has become simpler, that viscous term has vanished, equation is now looks much smaller, much neater, okay. Of course, simpler, but the major difficulty in solving the Navier-Stokes equation, which comes because of the nonlinear nature of the equation, that still remains, because this still remains nonlinear. And eventually that nonlinear nature is not associated with viscosity. The nonlinear nature is associated with the Eulerian description of the motion, the way we have defined fluid velocity. We have defined fluid velocity at a point, and consequently this nonlinear term are present in the mathematical equation. So, they will be present whether the flow is viscous or inviscid. Also see that there is another change, very important change, a very significant change. While the original Navier-Stokes equations, the governing equation for viscous motion is a second order equation, the second order differential equation, it contains that Laplacian operator which is second derivative. So, the Navier-Stokes equation was second order equation, while this is first order equation. There is no second derivative term, and then what is the difference? That in second order bound differential equation, or to solve second order differential equation, we need two boundary condition. Yes, we need two boundary condition, but for first order we can satisfy only one. Since the actual problem, this is just a simplification and approximation that is quite justified when Reynolds number is high, the approximation is quite justified, but due to that approximation we have reduced our equation by one order from second order to first order, and that second order, the two boundary condition, that is of course the realistic situation, the actual situation, the two boundary condition. But now we can satisfy only one. the one of the boundary condition will remain unsatisfied, you cannot satisfy that. What are these two boundary conditions? Again considering flow over a body, the boundary condition is that there is no relative velocity with respect to the body. There will be no relative velocity between the body and the fluid, which needs both the tangential component of the velocity as well as the normal component of velocity will remain same, or if the body is at rest, both of them are 0. The normal component of the fluid velocity on the surface of the body and the tangential component of the fluid velocity on the surface of the body, both of them are 0, assuming the body is rest, otherwise they have same magnitude. These two boundary conditions we cannot satisfy the two, only one we can. And in an inviscid flow, this is, see, out of these two, that one is not penetrating and the other is not slipping. Obviously, the not penetrating one is seems to be more natural. So, only that we can solve. In the Euler's, if we solve these Euler's equations, the inviscid flow equations, we can only satisfy the boundary condition that the normal component of velocity or normal component of the relative velocity is 0, but the tangential component of the relative velocity 0, that we will not be able to satisfy. In that case, there will be a slipping between the fluid and the body, the fluid will slip over the body. That condition cannot be satisfied. And this change is of course a very significant change, that one boundary condition we will not be able to satisfy. If we solve this equation or if we solve the flow as inviscid flow, we will not be able to satisfy that 0 relative tangential velocity boundary condition. And consequently, the solution that we will get will have some difference from the reality. Any inviscid flow solution in which we can satisfy only one of these boundary conditions, which is normal component of the relative velocity 0, that is what will be satisfied, normal component of tangential velocity or relative tangential component of relative velocity, that will not be satisfied, there will be a slipping, and as a result the practical solutions will never be obtained. Even though it appears that this approximation is very well justified, our Reynolds number is very large, and so we can really see that the term is very small. So, it appears that even though it is very small, it affects near the body is always significant. On the body surface, its effect is always significant. However, we will come to that part later on. There are techniques by which we can take the effect of it on the body, but treating the flow otherwise inviscid. What really happens is like this: this high Reynolds number flow, where we are neglecting the viscous term, which inherently means that both the coefficient of viscosity as well as the velocity gradients are small. Eventually, whatever large the Reynolds number is, this gradient is not really small on the body surface. So, on the body surface itself or very close to that body surface, even at high Reynolds number, the velocity gradient are large, and consequently that viscous stresses are present near the body surface. They may not be present a little away, maybe it is present only, say, thinking about an aircraft which is quite large, maybe within 1 millimeter or few millimeter from the body surface this effect is present, but after that it is not present. Anyway, let us forget this. So, we see that for a very high Reynolds number flow we can neglect the viscous effect. However, the resulting equations still remain nonlinear and which are again extremely difficult to solve. And to be precise, even the Euler's equations also have only limited exact solutions. Even these equations cannot be solved for general boundary condition for this problem. The equation is still remain unsolvable. For any given arbitrary body, the inviscid flow about that body is still unsolvable. The equation cannot be solved except few simple cases. So, we look for further simplification. Okay, the simplification must be justified. It is not that we just go on dropping. We will drop only when it is justified. As the viscous term we have dropped because it is justified. Now, to do that, let us go back what we discussed earlier. We said that in general the velocity field, fluid velocity field is superposition of three contribution: velocity field associated with an isotropic expansion, velocity field associated with a rigid body rotation, plus a velocity field associated with no expansion, no rotation, which includes even a uniform flow. Now, in a case in incompressible flow, now we have seen that there is no expansion. When the flow is incompressible or the fluid is incompressible, then the rate of expansion is identically 0. That is the continuity equation. An incompressible flow cannot have any expansion. We will also now see that if the flow is inviscid under certain conditions, it will become irrotational as well. That means, there will be no rigid body rotation. So, if the flow is incompressible inviscid and then it becomes irrotational, then the velocity field is simply made up of a velocity field which has no expansion, no rotation. That is just a pure solenoidal irrotational field, which we earlier denoted by that small v, and that will now be the complete velocity field. And just the condition of continuity and condition of irrotationality showed us that this velocity field satisfies the Laplace equation. We see that this Euler's equation changes to the Laplace equation if the flow is already you have started incompressible and inviscid, and if you can see that show that this is irrotational as well, then this flow will become a potential flow, for which the boundary condition again will be divergence of u equal to 0. That is the only boundary only governing equation.